So we're severely overcharging these cells right now. There it is. Yes, we got it. Hey guys, welcome back to another episode of Will It Fail? In today's video, we're going to find out if a circuit breaker or fuse can protect your battery from certain disaster when connected in parallel. So both of these batteries are charged to 100% state of charge. We're going to connect them in parallel and discharge one of them in 25% increments until enough current flows between them in order to cause a simulated failure, or until the wheels fall off. I've had my 2 ampere time batteries connected in parallel for over a year now and have been using them on the daily. And when I first connected them in parallel, I installed a 100 amp circuit breaker in between them just in case. And practically every 48 volt rack mount battery out there, SOK, EG4 and others, have a built-in circuit breaker. But very few, if any, 12 volt and 24 volt batteries on the market have no such feature. Instead, it's left up to the user or the BMS to handle this job. And I think the BMS should be your protection of last resort, and not relied upon as your frontline defense from potential disaster. We hear it all the time, right? Always charge your batteries to the same state of charge before connecting them in parallel. But what happens if you don't? Let's just say one of your batteries shuts down for some reason. Cell drift perhaps? And you don't notice it for days. Do you think you can just reconnect it to the bank?
Right? Right! Wrong!
But you do it anyway, without checking the voltage.
You go to plug this baby in, and you just happen to be soaking your bunions in a bucket of water.
And bam! 600 amps are flowing from the other batteries into the one battery. So should you add a circuit breaker or fuse in between your batteries? Let's find out. I bet you'll find the results surprising. Okay, so for our test setup, we have 2 identical batteries and they are connected in parallel. You can see the batteries are exactly charged to 100% and they are connected via this breaker, which is currently in the off position. This is a 100 amp breaker, and this battery on the left we're going to discharge in increments of 25%, so 100%, 75, 50, 25 to 0. And this battery on the left is connected to the inverter only, so when the breaker is broken, we'll only be drawing power from this battery only. Let's connect the breaker. See how much power we get flowing between the batteries. Okay, we're down to 2.7 amps. We can see that this one drew down and this one is at 100%. This is our baseline. We're going to be at less than an amp essentially. So we're going to break this breaker. Now we have 0 amp flow. I'm going to turn on our inverter. And we're going to run this down to 75% state of charge. Okay, we're pulling 150 amps now. We'll come back when this reads 75%. I'm thinking for sure one battery at 75% state of charge and the other at 100% would be enough difference to trip the breaker. But LiFePO4 cells have a very flat discharge curve, thus allowing for a fairly large difference in charge capacity, but not necessarily a large difference in voltage. Check out my video on charging and balancing for more info. Alright, we are back and we have reached the first stage of our test. This battery is at 75%. Well, these cables are nice and warm, not too warm. I swear, 12 volt. This is crazy. This is why I really don't like to mess with 12 volt. It's just so many amps, you know. You gotta have big cables, you gotta have everything big. Which is why I would say if you're gonna do 12 volt, you definitely want to have more than one battery in parallel so that you're not stressing the batteries out so much. Alright, so let's continue with our test. So this one's at 75. We're going to turn this one on. Our breaker is off. So we should see no current flow currently between these batteries. We're going to watch our amps and there is 0 flow. Okay, so we're going to turn our breaker on, and what do you guys think it will be? How much current will flow from this battery into this battery when this one's at 100% state of charge and this one's at 75%? So there's a 25% disparity. But remember, our voltage is at 13.29, so we're still in the 3.2, 3.3 volts per cell, which is in the voltage curve of a LiFePO4 cell. which, yeah, we might not see anything until we get down to like 25% or something because of that voltage curve. It just stays flat until the very end. So let's try it. Let's see what happens. Here we go. I'm going to flip the breaker. Whoa. Okay, so it shot up. Wow. I was surprised in the break. Okay, so it's not enough to trip the breaker. Remember, we have a 100 amp breaker. So we're trying to get this breaker to, open up and break the circuit and essentially protect the BMSs. So the BMSs are configured for 150 amps. And they can sustain more than 150 amps for about, I think it's set for 10 seconds. I have it set relatively short because I don't want to destroy the BMS. So we quite didn't do it at 75 amps. So we're going to continue the test. We're going to bring this battery down to 50%. All right, we're going to break it and we'll start the inverter up again. So we'll be back. It takes about 35 minutes to draw the battery down by 25% using this space heater. We are drawing a constant 1400 to 1500 watts from the battery. Okay, so let's do our 50% test. We went a little bit below, but that's okay. So what do you guys think? How much current is going to flow from our control battery to our test subject? You ready for this? Here we go. How much is it going to be? $20 amps, 30 amps? Come on, 30 amps. Look at the state of charge went up. When we were at 75% state of charge, it spiked to 100 amps. Yeah, there's a continuous draw. And that's greater than the last test, so let's stop this test and we'll go down to the next phase. So we're going to draw this battery down to 25%. There we go, no current. Well, 25% is where the voltage curve drops off, so hopefully we'll see some action soon. Okay guys, we are back and we are at 25% on our test battery. And this thing is pretty hot. It's over 100 degrees. Let's find out. Here we go. Kind of getting scared. We're getting down there. 25% versus 100% state of charge. Here we go. We're gonna connect them in parallel. Oh, come on. This is a big letdown. But look at, we're still at, look at the voltage. Look at this. So relatively speaking, we're only 0.1 volt difference still. That goes to show how steady the discharge curve of this particular chemistry is. I mean, look at that. There's hardly any difference in voltage still. Look at, we're pulling 25 amps. It's just a little bit more than 50%. So let's do it again. Let's drop it down. It's going to get interesting once we go. I think next step we're going to take it down to about 10%. Congratulations if you are still watching by this point. I promise we will see some interesting stuff soon. Do not try this, as it can be dangerous and damaging to your battery or BMS. This is for educational purposes only. Are you getting tired of this song yet? Alright guys, we are back and we are down to 10% on our test battery. This whole battery is pretty warm from discharging for almost 2 hours now. Look at our voltages now. We're now 12.8 and 13.3. So we're definitely getting down there. We should start seeing some fireworks, hopefully. Ironically enough, we're still in the 3.2 voltage range on our BMS. So, who knows? We might not see much. $28, ooh, 57, 55, 54. So it's getting up there. But still, that's not that it's not that great, you know. That's definitely not damaging. I mean, 50 amps really isn't much at all things considered. There we go. So we have a negative draw on our control. And a positive influx on our test. So let's break the connection. We're going to draw it down to 5%. Alright guys, we are back and we are getting down to the wire here. Look at this, 4% state of charge on our test battery. And look at our cell voltage, 3.1. So we are below the 3.2 threshold. So on our discharge curve, we get that sharp decline from 3.65 down to about 3.40. And we settle in 3.2 and 3.2 all the way down, as you can see, to like 10%. Then we get a sharp drop off below 3.2. And that's where the amps, the transference should start increasing exponentially when we connect these batteries in parallel. So let's see some fireworks. Let's see what happens. 4% versus 98%. Here we go. Can we get it? 49. 70. Oh man, 70. Dang it, so close. We're gonna have to push it. What do you think? 2%? Yeah, so let's draw it down to like 2% and then see what happens. Okay, so we are back and check this out. This is insane. Look at this. This is basically empty, right? This battery is full, 100%. But look at this. The other thing to consider is not so much how much is going through this battery, but how much is going into this battery. These particular cells are rated for 0.25 charge C rate. That's about 70 amps. So you don't want to exceed that. Obviously doing this one time won't damage your battery, but if you were to continually dump in more than 70 amps, you will degrade the lifespan of your cells. And even in the BMS, look at the BMS. So our continued charge current, that's a default by JK, 70 amps. Okay, so we got 30 seconds of 70 amps before the BMS will trigger OCP error essentially and shut down. So we got 30 seconds for this thing to trip. We're going to do the big one, see what happens. Are we going to get 100 amps? Can we get 100 amps? Should we even do 100 amps? Of course we should do that. That's the whole point of this test. If I can't get 100 amps, I haven't done my job. Here we go. Watch the breaker. Watch the amps. Here we go. 44. Ooh, 129. All right. This is good. This is good. All right, countdown timer for the BMS. The BMS will shut down in 30 seconds. This thing hasn't tripped yet. Kind of disappointing. We're going to wait for the BMS. We're going to give it 30. Oh, look at that. We got an Air 3. And the BMS took over. Look at that. This thing didn't even do anything. We had to rely on our BMS. Oh, so our BMS just came back on because there's a delay and it cycles back on. So we're back to 100 amps. I'll give it another 30 seconds. So a DYI BMS, like the JK BMS, right, it's going to keep on doing this. It's got a delay in there. It's going to keep on cycling on it. That's not good for the cells, not good for the BMS to do that. A lot of the retail batteries you see, we're going to shut this off. A lot of the retail batteries out there, like Amber Time and basically every battery that's out there, they have our BMS that, as far as I know, when it encounters an error, it will not, it doesn't have a cooldown time. It literally goes into like a sleep mode. Like there's a problem, goes into safety mode, and the only way to wake it up, and this could be, I don't know if it's for this particular scenario, but I know it's for an over discharge, like you discharge the battery too low, it'll go into sleep mode and you'll have to have a special charger. In fact, one of these box chargers that can essentially wake it up. So if you encounter such a scenario where this happens and your battery shuts down, you'll kind of be screwed unless you have one of these chargers to get this thing to wake back up. So that's something to consider. I don't know what to do about this. I'm going to have to draw this down to 1%, I guess. Or even further. Alright, this is getting some crazy numbers. So we basically ran this battery down to the BMS stopped. Okay, we are rocking it till the wheels fall off here. So, looking at our BMS, we're set to 70 amps. We're going to increase our delay. So we'll give it 1 minute. With a 30-second cooldown. Alright, so both batteries on. This time we got our clamp meter. We're at 0 and we're at 97. Cell voltage is 2.8. So we should get this should run for at least a full minute, over 100 amps. So hopefully we can get the breaker to trip here. Alright, here we go. $80 amps, 200 amps. Wow, look at that. 209. But I'm really disappointed in this breaker. 188. Yeah, this is not good for your battery. We're charging almost double. Oh, what happened? This one went? Okay, this one went in the air. I think we got an over discharge error on this one. Alright, let's do a reset here. Let's see what we got. Yeah, discharge over current. So we're really making the BMSs really protect these cells. You can see, and you can see all the different ways in which BMSs protect your cells. There's at least 6 different ways that they protect your cells. Alright, we're going to restart this test. We got 30 seconds to discharge before the BMS kicks out. And we got a minute over here. Should probably match them up, but alright, here we go. Let's see what happens. $193 amps. 187, 173. So we're severely overcharging these cells right now. There it is. Yes, we got it. Awesome. But that's not bad. I mean, all things considered, what was that? 20 seconds? 20 seconds and the breaker did its job. Well, oh yeah, it's pretty warm. The breaker is warm. Wow. Well, it's a thermal breaker, so it has to get hot. That's the way it works. You know, depending on what battery you buy and what the settings are on the BMS, at least you can kind of sleep better at night, knowing you have an extra layer of protection. Alright guys, we're back for one last test. We have a 100 amp AMG fuse. So we're going to see how fast we can blow this AMG fuse. The default settings for the BMS are 15 seconds for the overcurrent protection. The breaker took 20 seconds, so it was too long. It wasn't able to protect the BMS. So we're going to see if we can get this, hopefully this fuse will blow faster than the breaker would. Let's see what happens. I'm going to stand back in case this thing blows junk everywhere. 127 amps. Yeah, the BMS kicked in. That sucks. Alright, final test. Here we go. Let's see if we can hear that thing. I'll just put the mic right on there. How about that? Alright, here we go. I'm going to hit the breaker and I'm going to stand back. Did it blow? That was quick. Do we have an error on the BMS? Let's check the BMSs. I don't see any errors. Well, if that's the case, it handled it pretty well, I would say. Let's check the fuse out. Let's do a quick continuity test. Nothing. I think that fuse blew. It didn't explode or anything, it just quietly went. I was kind of surprised. I thought these fuses were crap, but I would still never use them in a solar system. There's better fuses out there, such as Victron's mega fuses or an ANL fuse. Alright, so one last test. We're going to see if we can charge the battery. We are currently charging the battery at 9 amps by subverting the fuse here. I'll connect the charger to the fuse end. This fuse is definitely shot. Yeah, so there you have it. It took about 5 seconds for a fuse to blow versus a breaker. So personally, I like to have both devices in my circuit for my circuit protection, because a fuse obviously doesn't give you the control to be able to disconnect a particular battery from your battery bank to do maintenance or what have you. And the fuse obviously blows quicker, gives you that quick response, and that's what you need to protect your BMS. So in short, you should have something besides the BMS between every battery, whether it's a breaker or a fuse or a combination of both. Personally, I like to use both because the breaker allows you to disconnect the battery from the bank, and a fuse allows for that quick response when something bad happens. If you are connecting more than 2 batteries in parallel, I would recommend running each battery to a fused busbar like the one you see here. A fused busbar allows a connecting point to keep the battery cable in place, and at the same time link it to the busbar via the fuse. Be sure to use equal length cables for each battery. Be sure to use a quality fuse like Victron's Mega Fuse, as they are designed for such a job. If you are looking for a higher end smart busbar, take a look at Victron's Power In products or Lynx distributor. From what I can tell, the Power In does not come with hardware to support fuses. It seems to be a Lynx distributor without the guts. Basically, a nicer busbar. But you can add fuse capability with a simple hack. You can find a link to Nate's video from Explorist.life in the description below, detailing the hack. The Lynx distributor is a modular smart busbar with 4 locations for DC fuses. It will monitor the status of each fuse and indicate its condition with a LED on the front. Links in the description below. Well, I hope you found this video useful, and as always, thanks for watching.